concentration is again going to be X. Let's erase some stuff here. Okay. So now to solve for the concentration of hydroxide, we're going to again make a K. This is the base, and we're writing an expression for Kb. Kb for this base is going to be the concentration of BH+, which is going to be X, times the concentration of hydroxide, which is X, all over 0.0649 minus X. This is going to be equal to the Kb value. Now, we're not given that for this base here in the problem, but what we do know is we know Ka for the acid. So to find Kb for the base, the conjugate base of that acid, okay, Kb is going to be Kw divided by the Ka value for the acid. And when you do that, you find the Kb for the base is going to be 4.17 times 10 to the negative 10th power. So we're going to put that in here, 4.17 times 10 to the negative 10th power. We can see this is way small, so the change here is going to be insignificant. But that goes away, so it just becomes x squared over 0.0649 equals the Kb value. If we solve for x, which is concentration of hydroxide, is going to be 5.20 times 10 to the negative 6th power, which means POH, if we take the negative log of this, gives us 5.28, and then the pH by extension is going to be 8.72. That is the pH of the solution at the equivalence point. Now the question we want to ask ourselves, the last step, okay, after we've done this, let's check, does this make sense? At the equivalence point, does it make sense for the pH to be basic? The answer is yes. Because as we titrate, this is an acid, right? When this is neutralized, we've produced a base. Hence, we expect the pH at the equivalence point to be basic. And it is. So there we go. That's how you solve part B. Okay. Hopefully from there up to here, that makes sense. Okay. Then we go through and we're going to solve for another series of things here in the problem. So I'll erase over here and we'll go on to part C. Okay. Part C of the problem is asking, what is the pH at the midpoint of the titration? Well, something we know about titrations that's funny and something you want to remember. At the midpoint, the halfway point of any titration, the pH of the solution is going to be equal to the pKa value of the acid. Since we know the Ka value for the acid, this is very simple to calculate, and we can just figure out that it is going to be 4.62. pKa for that acid is 4.62, so that is the pH of the solution. That is nice, and that is easy. Okay, for problem D, okay, part D is something we didn't really talk about too much in class. It's what indicator would be best for this titration. To see which indicators would be best for the titration, we have to know what is the pH at the equivalence point. Because like we said in class, you want your indicator to change color at about the same pH as the equivalence point, so that the end point is the same as the equivalence point that we figured out that it is. So you want to find an indicator that's going to change color at a pH of 8.72. Well, something you guys should know. Indicators are weak acids, almost predominantly. They all have a Ka value, because they're weak acids, they all have a Ka value. And so they're going to change color when the pKa, okay, of that acid is equal to the pH. So what you want to do is you want to find an indicator whose pKa value is as near to 8.72 as possible. If you look in your book, the best indicators that are going to bracket this well are two things. This is in chapter 17. You can find the table, and the answers are either phenolphthalein, or if you look over there, orthocresolphthalein will also be a good indicator. Okay, so that's part D. On to the last, guys. This has been endurance trial. On to the last part, part E. This is the most difficult part of the problem, in my opinion. In part E, and we're not going to do each step. I'm going to leave a couple for you guys to do by yourselves. We will do together 2 parts. Okay, so what it says in part E is calculate the pH of the solution after adding 5 milliliters, 10 milliliters, 20 milliliters, and 30 milliliters of the base. And then sketch a titration curve. Okay. So this goes back to what we're doing here in the problem. Again, this is just, we're titrating our acid. Okay, so this is combining with hydroxide to give us the conjugate base plus water. Okay. Maybe I'll write this down here. we're going to make ourselves another ice table. So we have our acid plus hydroxide makes the base again plus water. Now to make this ice table with lowercase letters to show that we're working here in moles, with moles. Now what we know, we started here, we already said with a certain amount of the acid, we start with 0.005 moles of the acid. Okay, now in each step here, as we're adding sodium hydroxide, what we're going to be doing is we're adding hydroxide. That hydroxide is going to react with the acid, and so the moles are going to be decreased. In the first step, we're not adding 30 milliliters, we're adding 5 milliliters here of the base. We're adding 5 milliliters of the base. We need to calculate how many moles of hydroxide we're adding. Well, the way we would do that, okay, we take the volume 0.005 liters, it's 5 milliliters, times the concentration of the base, which is 0.185 moles per liter, and we see that comes out to be 0.000925 moles of hydroxide. So that is what we're really doing when we add 5 milliliters of the base to the solution. We're adding this many moles of hydroxide. Okay, so I didn't write this big enough. We'll just write this here in a different colored pen so we understand what it is. It's going to be 0.000925 moles of hydroxide. Okay, we don't have any of this, and we don't have any of this to start with. Now, when we add this many moles of hydroxide, these are going to react quantitatively here with the BH plus, the weak acid here, and so the change for this is going to be minus 0.000925 moles. This number of moles is going to be going down. So at the end of this step, after it has reacted fully, what we have left is we're going to have 0.004075 moles of our acid left. And of course, we're not going to have any hydroxide left. It's all going to react. And we're going to produce some of the base, which is going to be 0.000925 moles, and then water we don't care about. Okay, so we have this much of the base, and we have this much of our acid. It should be obvious to you guys at this point, if we have the acid and we have its conjugate base, what we really have is a buffer. So in order to calculate the pH, guys, we are going to apply the Henderson-Hasselbalch equation, and it is this. pH is equal to pKa of the acid plus the log of the base, the ratio of the base over the acid. pKa for the acid is something, I didn't write it down, but if you go through and you solve, oh wait, I did, okay, 4.62 plus the log of the ratio of the base, which is going to be 0.00925 over the acid, which is 0.004075. Okay, if you calculate that, the pH there, you will see that gives you a pH of 3.98. Okay? The process is going to be similar for whether you're adding 5 milliliters, 10 milliliters, 20 milliliters, etc. We're going to look at together what happens when you add 30 milliliters of the base, because that's a little bit different.